So, in interference, we have derived the expression for the bandwidth. Bandwidth and fringe width both have the same meaning. In case of interference, it is the distance between the two consecutive bright band or two consecutive dark band. It is one such definition. It is the distance between the two successive minima or two successive maxima, secondary maxima. So, in case of interference, the bandwidth beta we have derived, it is given by lambda capital D upon small d. This is the relation. Same relation is for diffraction pattern also. So, we have to derive that formula. But what is the change? Except this is called as a central maxima. Central maxima has spread from this angle to this angle. So, these are also two minima, secondary minima. First minima on right hand side, first minima on left hand side. So, this is also fringe width. But this fringe width and this fringe width have different values. So, in case of interference pattern, the bandwidth is given by this much and equal bandwidths are present, whatever may be the position of the bright and dark band. But in case of diffraction, this is not the case. The bandwidths are not equal all over the diffraction pattern. And therefore, we have to consider the bandwidth or fringe width in diffraction pattern like this. So, first we will derive the expression for this. It is called as the angular bandwidth. Linear bandwidth. म्हणजे डिफ्रॅक्शन पॅटर्नमध्ये आपल्याला दोन प्रकारचे बिट्स कन्सिडर करायचे आहेत. एक म्हणजे दिस अँग्युलर बँडविड्थ आणि लिनियर बँडविड्थ. सो फर्स्ट वी आर गोइंग टू कन्सिडर द लिनियर बँडविड्थ. लिनियर fringe width. W or it may be denoted by beta. Both type of symbols are used. Definition. Linear means it is a distance and angular means it is a angle. Definition. The distance between two successive, two consecutive secondary minima or secondary maximum. Secondary maximum. So this is the definition. So these are two secondary minima. These are two secondary minima. So this separation is called as the bandwidth. So in this figure, I will add this distance is the bandwidth beta, or this distance between the two successive maxima. This distance is also called as the beta. Therefore, now we are to derive the expression for fringe width. W or beta. We will use symbol beta. In the book, W symbol is used like this. Of course, we are going to derive the expression for secondary maxima and minimum like this, sir. So we will use the same figure that we have used for interference. This is say nth minima. This is n plus 1th minima. So these are two successive minima. So this distance is bandwidth beta. This distance is the yn. Yn d for dark. This distance is yn plus 1 d for dark. So positions of nth and next, that is n plus 1 minima are given by yn into d upon capital D is equal to n lambda. Therefore, yn is equal to n into lambda into capital D upon small d. So this is equation number 1. Similarly, now next diagram, yn plus 1 into d upon d is equal to इकडे पण n plus 1 बँडचा नंबर आपल्याला घ्यावा लागेल. हा पार्ट डिफरन्सचा फॉर्म्युला पण इथे केला. Therefore, yn plus 1 is equal to n plus 1 lambda capital D upon small d. This is equation 2. So by definition, beta is equal to distance between nth and n plus 1 dark band, minima, secondary minima. From center O. And therefore, beta is equal to yn plus 1 minus yn. So this is equal to n plus 1 into lambda capital D upon small d minus n into lambda capital D upon small d. So lambda common, capital D common, small d common into bracket n plus 1 minus n. So plus n minus n cancel. So this is equal to lambda capital D upon small d. So this is the expression for the fringe width. So fringe width W is given by equation A. Same formula can be derived for secondary maxima also. So only one method is sufficient, but you can use also that second method. So this is the expression for the fringe width of the diffraction pattern, like this. Now, one more method using dark band, using bright band, or using locations of nth and n plus 1th secondary maxima. Beta or W is equal to y n plus 1 b forward minus y n B for right. So similar to this, it is given by n plus 1 half into lambda capital D upon small d, and this is minus n plus 1 half lambda into capital D upon small d. Odd multiple of lambda part differential value is odd multiple is. So if we open this bracket, then n plus 1 n plus 1 half n plus 1 half will get cancelled. It is again lambda capital D upon small d. So same formula is derived. So equation A and equation B gives the fringe width for secondary maxima or secondary minima. That is for secondary minima, for secondary maxima. Both are same. Now, so the value of the bandwidth is equal for secondary maxima and secondary minima. But the case of central maxima is different. So you can give that value separately. So in this figure, these are the two successive minima on both sides. So width of the central maxima is somewhat broad, and it is denoted by beta d. Fringe width of central maxima it is denoted by beta, but it is for n is equal to 0, therefore it is denoted by beta 0. Definition. Each definition, it is the linear distance between first secondary maxima minima on either side of center of diffraction pattern. So this is first minima on left hand side. This is first minima on right hand side. So it is like this. Beta 0 is equal to by 1 d on right hand side minus by 1 d on left hand side, and therefore this is equal to 1 into lambda into capital D minus 1 into lambda into capital D upon small d. So this is equal to 2 times lambda capital D upon small d. So that is equal to beta 0 is equal to 2 times beta. जे बाकीच्या diffraction pattern की width है beta, त्याचे double ही width आपल्याला मिळते. So beta 0 we have proved that beta 0 is equal to 2 times beta. हा क्वेश्चन सेपरेटली पण विचारला जातो, तो आपल्या नोट्स मध्ये पण दिलेला आहे. So either you can use this minus sign, minus will get cancelled, or you can cancel only magnitude. म्हणजे second method अशी पण देते. Distance on this side, on the left side of center, distance on the right hand side of the center, and therefore on left hand side of origin or center, the values are taken as negative, and therefore this minus will become plus. So width of the center maximum beta 0 is equal to 2 times beta. आपल्या नोट्समध्ये डिस्टिंग्विशचं एक टेबल दिलेलं आहे, तर त्या टेबलमध्ये हा पण एक पॉईंट आपण घेतलेला आहे. सो इन केस ऑफ इंटरफेरन्स द बँडविड्थ आर इक्वल एनीवेअर इन द interference pattern, but in diffraction pattern this is not the case. The width of the central maxima is twice. The width of the central maxima is twice the width of the remaining diffraction pattern, like this. So beta 0 is equal to 2 times beta, and beta is given by this equation for secondary minima, for secondary maxima. So this is about the linear width, linear fringe width. Now we can also give the formula for angular bandwidth, and that angular bandwidth is defined again in the same way. It is a distance between the two successive secondary maxima or secondary minima. Distance ऐवजी फक्त तिथे अँगल टाकायचा. इट इज द अँग्युलर सेपरेशन बिटवीन द टू सक्सेसिव्ह सेकंडरी मिनिमा or two successive secondary maxima. So in the same way we can derive that equation also. So that pattern is not given in our notes directly, but we will derive that relation like this. So we have seen about the linear width. Now let us see about the angular width. So you please add this part. Angular fringe width W. The angle between the two successive secondary minima and secondary maxima is called as the angular fringe width. It is denoted by symbol पण change म्हणतात येईल. It is denoted by theta. So angular position of n and next n plus 1 minima are given by theta nd is equal to. This is the formula for first secondary minima. We have to give for nth minima, so it is equal to n into lambda upon small d. This is equation A. Theta n plus 1 d is equal to n plus 1 into lambda small d. This is equation B. So B minus E gives angular bandwidth theta is equal to distance angle between the two successive minima, and that theta is equal to n plus 1 into lambda upon small d minus n into lambda upon small d. So if we open the bracket, this is equal to, so theta is equal to this. So this is equation capital A. So capital A gives equation A gives angular bandwidth for secondary minima and secondary maxima. Secondary minima or secondary maxima. Now here we are seeing the fringe width of the central maxima. आता इथे आपल्याला angular bandwidth आहे. So angular bandwidth angular fringe width of central maxima it is denoted by theta 0. So it is the linear distance, it is the angular separation between first secondary minima on either side of the center of the diffraction pattern, and therefore theta 0 is equal to theta 1 plus theta 1, this theta 1 and this theta 1 on other side, so that is equal to lambda into d plus lambda into d. Either you can write like this or this value may be negative. So 2 times lambda into d, and therefore theta 0 is equal to 2 into lambda into d, or 2 times theta. So the width of the angular width of the center maximum is again 2 times the angular width of the remaining diffraction pattern. So angular width of central maxima theta 0 is twice the angular width of remaining diffraction pattern. Central maxima should remaining diffraction pattern. So beta 0 is equal to 2 times beta is equal to 2 into lambda capital D upon small d, and theta 0 is equal to 2 times theta, that is equal to 2 into lambda upon small d. So these are the expression for the linear width and angular width of the central maxima. This is the bandwidth of the linear bandwidth of the diffraction pattern. This is the angular bandwidth of the diffraction pattern, like this. So these relations can be used for solving the problem. So this part is not given in our notes, so you please add it. So we know the relation for angular bandwidth and linear bandwidth, like this. Now so when we are using two slits, what will be the nature of the diffraction pattern? 2 slits, 3 slits, n slits. The figure arrangement will be same. So in this case, there are two phenomena. One is a diffraction phenomena, because this lambda comparable with d condition is satisfied, and second one is the interference phenomena, like a double slit, Young's double slit experiment. So this Fraunhofer diffraction for two slits resultant diffraction pattern is the combination of the resultant diffraction pattern is the combination of first the diffraction pattern of individual slits diffraction pattern of individual slits under condition lambda is comparable with d, and second interference pattern between the light waves from two slits but having variable intensity at brightness. So resultant diffraction pattern is like this. So if you draw the figure, the arrangement is like this. This is the angle theta and this is the intensity. So it is again the intensity distribution pattern like this. So the diffraction pattern, this first part of the individual slits is like this. This is the first minima, center maxima, like this. Like this. So in between this is this part. And now inside this there are interference bands like this. These are interference bands. Interference bands like YDSE, young double slit experiment. So this part is here. So it is the envelope like this. So it is a combination of two patterns, interference pattern and diffraction pattern like this. So this is about the diffraction pattern of the double slit experiment like this. So now let us differentiate between the interference pattern produced by YDSE, Young double slit experiment, and diffraction pattern produced by the Fraunhofer diffraction pattern produced by the single slit experiment like this. So first point of difference, we have given the nature of the pattern, interference pattern of YDSE and interference pattern of Fraunhofer diffraction using the single slit. So in this case, beta is same everywhere. So from figure, you can use some points. Beta, bandwidth beta, all the interference bands are of equal bandwidth. Beta and third point, and equal intensities, that is I0 is equal to I1 is equal to I2 is equal to I3 is equal to I4 is equal to dot 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 dot. Now on this side, the diffraction bands are of unequal bandwidth because beta 0 width of the central maxima is equal to 2 times beta and unequal intensities because I0 is greater than I1 is greater than I2 is greater than I3 is greater than I4 like this. So intensity goes on decreasing. So from the diffraction and interference pattern we get these simple differences like this. So fourth point. These minima are having completely zero intensity. The minima in the interference pattern is perfectly dark. Minima in interference are perfectly dark, means zero intensity. इथे तसं नाही, डार्क बँडला पण मिनिमाला पण काहीतरी इंटेन्सिटी असते. द मिनिमा इन डिफ्रॅक्शन has some non-zero intensity, so they are not perfectly dark. They are not perfectly dark. Fifth, location of nth bright band is Yn is equal to n into beta n into lambda into capital D upon small d. Location of nth dark band is Yn is equal to n minus half beta, that is equal to n minus half into lambda into capital D upon small d. So the values of part difference are obtained from this equation. So better way we will remember this difference in case of values of part difference. Part difference for nth bright band is PD is equal to Yn into D upon D by small d upon capital D is equal to n lambda. Part difference for nth dark band is nth dark band is difference is equal to yn into d upon d is equal to n minus half lambda, n minus half lambda, like this. On this side, for nth secondary minima, part difference is equal to yn into d upon d is equal to, इकडची कंडिशन इकडे जाते, n minus half into lambda, sorry, 2n minus half. For minima it is n lambda. इकडची ब्राइटची कंडिशन इकडे मिनिमा साठी, कंडिशन तीच आहे पण ही ब्राइट बँड साठी ती डार्क बँड साठी. For nth secondary maxima, part difference is equal to yn into d upon d is equal to n minus half 2n minus 1 into lambda by 2. N starts from 1. N is equal to 1, 2, 3, 4, like this. Like this. So the values of part difference are exactly opposite. Even multiple of lambda by 2, even multiple of lambda by 2, but it is for secondary minima, it is for maxima, bright band, like this. So remaining differences are not that much really important. So one more important point is this. Interference is not related with phenomenon of resolution. So next we are going to see this point in detail. Diffraction phenomena. Diffraction phenomena is used to explain resolution phenomena. Since I1 is equal to I2 is equal to I3 is equal to IN, so large number of interference bands are observable on this side. Since I0 is greater than I1, greater than I2, greater than I3, greater than I4, therefore very few diffraction bands, are observable, like this. So these are the main differences. Then this interference pattern, it is produced by two different sources. They are coherent sources as well as two. Here the part of the same wavefront is used. एकाच वेवफ्रंटवरचे दोन पॉइंट इथे यूज केले आहेत, तो एक पॉइंट आपल्याला देऊ शकेल. सो दीज आर द पॉइंट ऑफ डिफरन्सेस बिटवीन interference phenomena and diffraction phenomena, like this. So this point number 7 is important. Diffraction phenomena is used to explain the resolution phenomena. So this resolution phenomena we are going to see in detail from next lecture. It is also related with the new technology of medical sciences like CT scan, etc. And therefore this this resolution phenomena has importance in medical sciences today also. So we will see in detail from next lecture. Okay, we'll stop here today. So we have seen the problem on interference last time. Now the remaining problems are only related with the diffraction and resolution phenomena. So this problem session for diffraction will be separate.